invite our next speaker, Hawkeye Ma, who will present the paper Exploring False Hard Negative Sample in Cross-Domain Recommendations.
Good afternoon, everyone. My name is Hawkeye Ma. I'm a third-year PhD candidate in Shandong University, and I'm also interning at RecSys Center. I'm glad to present my paper of exploring false hard negative sample in cross-domain recommendation. We will introduce this work in 5 sections, including introduction, motivation analysis, our proposed real hard negative sampling framework, experiments, and conclusion. The first section is the introduction. First, I would like to introduce the negative samples in recommendation. Recently, personalized recommendation models extracts researchers' attention due to its ability to provide the appropriate items to users. Real-world recommender usually has more than millions of users and items. Its personalized demand and the data sparsity make it impossible for all users to interact with all items. However, like other classical supervised learning tasks, recommendation models need positive and negative samples for training. This prompts us to explore advanced negative sampling methods. Under this common data sparsity situation, cross-domain recommendation is a straightforward but effective technique to transfer useful positive signals from the source domain to the sparse domain, while existing methods only focus on the feature-level cross-domain correlations with the randomly selected items from the target domain, overlooking the negative knowledge from the source domain and ignoring the cross-domain differences at the simple level. To the best of our knowledge, this work is the first negative sampling framework in cross-domain recommendation. We illustrate some classical negative sampling strategies here, which can be classified into static negative sampling strategies and hard negative sampling strategies due to the fixed sampling probability distribution or not. For the static negative sampling strategies, UNS randomly sample items with equal probability. NCF assigns the sampling weights to items based on their popularity, and ENMF designs a known sampling training strategy to include all the items in training. For the hard negative sampling strategies, DNS dynamically selects the top-ranked item as the hard negative sample from the randomly selected item candidates. These methods are designed to avoid the false negative problem with the randomly selected candidates, which is unstable and uninterpretable for different data sets, making it challenging to effectively explore and utilize hard negative samples. The second section is motivation analysis. It is intuitive that more negative samples can reduce the impact of the false hard negative sample on the global gradient, thus benefiting the model's optimization. While too many random triplets will cause true hard negative samples to be joined in random samples, then we conduct experiments to verify this observation in a simple cross-domain recommendation task. As shown in the figure, we notice that the performance first increases and then decreases as the number of random negative samples gets large. We believe that the appropriate number of negative samples does achieve comprehensive optimization and elevates the impact of false negative samples. Then we analyze the effective mechanism of these negative sampling strategies. DNS and DNS asterisk oversamples the top-ranked items from the random candidates, makes GCF conduct the interpolation to translate the potential false hard negative samples into the real hard negative samples. These methods have a certain randomness in sampling, making it difficult to stably solve the false negative problem. Furthermore, they have failed to reveal the core of the false negative problem. The first problem is that which items can be considered as a false hard negative sample. And in the cross-domain situation, there is another problem. Is there the false negative problem in cross-domain recommendation? And if so, how should we find the false hard negative sample under the CDR setting? The third section is our proposed real hard negative sampling framework. We know it as real HNS. First, we will provide the definition of HNS, RHNS, and FHNS. HNS is that samples with more information than uniform negative samples, and their incorporation can aid the model's optimization. False FHNS denotes the items wrongly selected as negative samples, which will be clicked by users in the future. And the RHNS are the selected HNS that are neither too easy nor too hard. We have defined an equation that is HNS equal RHNS plus FHNS. The general RHNS cannot be applied to CDSR tasks that involve both multi-domain behaviors and temporal information, especially for those users who exhibit significant differences among their multi-domain preferences. Their transfer preferences are diverse with the mainstream transfer of all users. We call these users as outliers. As a result, the general RHNS may have the optimization specific to these outliers. Then we propose the following three hypotheses. The first is that items in close to the positive sample are more likely to be FHNS in CDR. And the second is that samples that bear a strong resemblance to the user's source domain representation indicates their transfer preferences and are more likely to be RHNS for outliers. And the final is that introducing all HNS at the beginning of the training process may lead to the computational wastage and suboptimal performance. The general FHNS and the cross-domain FHNS of real HNS are shown in the picture, where each star and the circle denote the user and item representation, and the brightness of colors indicates the item's sampling probability. In the left of the figure, general FHNS are close to the positive samples, and the general RHNS are close to the user representation. The middle part denotes the negative transfer in cross-domain recommendation. Users have different transfer patterns, with the mainstream transfer are viewed as outliers, who will be wrongly impacted by known outliers. And in the left part of the figure, cross-domain FHNS are related to known outliers in CDR, where for outliers, we select the items close to their transferred source representation as the cross-domain RHNS. As demonstrated in hypothesis 3, we leverage a curriculum learning framework to improve the generalization capacity and the convergence rate of CDR models. As shown in the left, we propose two types of curriculum learning methods, that is, optimization-based curriculum learning and filter-based curriculum learning. The former involves dynamically adjusting the proportion of RHNS in the negative samples to start with a smooth objective, enabling the fancier discovery of the global minima, and the later dynamically regulate the scope of general and cross-domain atom candidates to be filtered to elevate the inclusion of hard negative samples into the training process. The next section is the experiments. To demonstrate the effectiveness of the real HNS in CDR, we compare it with 6 hard negative sampling methods in 6 cross-domain settings. Limited by the page, we only show the game-to-toy and the toy-to-game setting. We can observe that first, real HNS significantly outperforms all baselines on diverse cross-domain settings. The second is that the improvements are larger with smaller n and rank-sensitive matrix. The third is that no hard negative sampling strategies can consistently outperform other methods on all datasets on the challenging setting of 20 negative samples. The final is that real HNS is more beneficial on dense to sparse setting. It is similar to the traditional CDR methods. With the aim to verify the effectiveness of different components in real HNS, we conduct ablation studies, and from the table we notice that first, existing hard negative sampling methods in dealing with FHNS are unstable. Only the high quality HNS are beneficial. The second is that the dynamic item-based FHNS filter can elevate the false negative problem in general RHNS, thereby including informative but challenging samples. The next is that the proposed cross-domain RHNS is potential for elevating negative transfer in CDR. And the final is that the dynamic user-based FHNS filter can accurately model the user preference with varying degree of multi-domain differences and regulates the hardness of RHNS. We conduct the universality analysis on DNS and mixed GCF besides the DNS asterisk on 4 cross-domain settings. From the results, we notice that first, real HNS achieves consistent improvements over DNS and mixed GCF on all data size. The second is that real HNS accomplishes incremental performance improvements of each component, which highlights the practical application of the general and cross-domain RHNS. The final is that due to the fact that mixed GCF can optimize the distribution of synthetic negative samples in the feature space, real HNS on mixed GCF can benefit more. With the aim to verify the universality of real HNS in different recommendation tasks, we adopt real HNS with a classical CDR model, DASL, a classical CF-based model, BPRMF, and a classical single-domain sequential recommendation model, SAS-REC. Based on this table, we notice that real HNS performs better than the classical HNS method DNS in all metrics of both single-domain and cross-domain tasks. And the next is that real HNS outperforms UNS largely on all NDCG metrics and hidden rate metrics with smaller k. And the final section is the conclusion. In this work, we review the underlying mechanism behind the current negative sampling methods. The proposed real HNS elevates the false negative problem inherent with a novel dynamic item-based filter in a curriculum learning framework. Meanwhile, real HNS introduces a cross-domain HNS to filter out the potential noise in cross-domain transfer. In the future, we will exploit the application of real HNS in other recommendation tasks, as well as reform it in a non-parametric manner. We will also explore the occasional HNS with the user's multi-behavior and items multimedia information. Thank you for your listening. If you have any questions, please contact me via the email.
Thank you. Thanks to our speaker. We have plenty of time for questions, so please.
Thank you for your representation. My research also focuses on negative sampling, but my research only in collaborative filtering. So my question is, in CF, we have some, mathematical analysis or theories show how hard negative sample affect performance. So do you have interesting or you have plan to analyze why hard negative sample can affect cross-domain in mathematics?
I'm so sorry that your question is that how negative samples affect the cross-domain correlation?
Yeah, by some mathematical analysis or theories analysis.
Yes, I get it. It's a good question. Actually, we have employed our real HNS on the CF-based method BPRMF like this table. Actually, we only employ the general real RHNS in our framework real HNS for the collaborative filtering. And then we also employ the proposed curriculum learning framework. But we have not employed the mistake analysis about the negative samples because our main contribution is to employ the negative sampling strategies in cross-domain recommendation. And the experiments on collaborative filtering is the aim to verify our universality of the proposed real HNS.
Thank you.
Thank you. Any other questions? While you're getting the courage to stand up for the questions, I'll read the question that we got online. So real HNS, several experiments in CF and sequential recommendations. This is what you presented. The question is, could you explain briefly how would you deploy your approaches?
Just in CF collaborative filtering or our cross-domain recommendation?
What you presented, how would you deploy it in a real scenario?
Okay. Let me find the page. Sorry. Actually, this picture is our method, and please image that all the items in the feature space have their fixed position, and then the general RHNS and the cross-domain RHNS select different candidate size in the feature space. And then we construct a sphere centered on the positive. I'm sorry. Perhaps it shows the wrong figure. In the center of the black circle, it is our target item, and then we construct a sphere centered with the target item, and then the sphere is
Sorry to interrupt you. I understand, but what is the difference between this research and its application in a real industrial domain, the deployment in a real industrial setting?
in other in other downstream tasks.
For example?
Yes, we have employed this method on the CF-based method and the single domain sequential recommendation methods. In this method, we don't have the cross-domain information, so we only used our proposed general RHNS with the proposed two curriculum learning methods.
Okay, thank you very much. Are there any other questions? Yes, please.
Hello. So me and actually Hawkeye, we are from the same college, and I have read this paper before. So thanks to this opportunity, I just want to ask some details about the negative sampling process. So that's my question. Thank you.
Sorry, could you repeat the question? Because I think none of us got it.
Okay, so my question is, actually it's not a question, I just want to know more details about the negative sampling progress. So that's my question.
Okay, so maybe we can move this to offline because I think more details would be just extending the time here. That's quite limited. So let's give another round of applause to Hawkeye Ma. And I welcome our next speaker, Jiajie Zhu from Akari University, who will present the paper Domain Disentanglement with Interpolative Data Augmentation for Dual Target Cross-Domain Recommendations.